Hello, my name is Vishal Bharti and I am from New University of Lisbon, Portugal. Before starting my presentation, first of all, I want to say thanks to the organizer of this conference who has invited me as a speaker in this conference. And I'm going to discuss about, in this presentation, I'm going to discuss about the role of Forster resonance energy transfer in the bulk heterojunction organic solar cell. The picture which I have pasted here describe the story of energy transfer in between the two polymers and how one polymer transfer its energy to the another and the another one generate more number of charge carriers, which overall enhance the efficiency of solar cells. So let's begin this presentation. This is the outline of my presentation. In this, first I will discuss about the solar cell, just discuss different technology about the solar cell, and then about the organic solar cell. This whole presentation is revolving around the organic solar cell. So I will discuss this topic in more brief about its organic solar cell history and their present prospect, how we can fabricate this solar cell, what's the working mechanism of this organic solar cell, what the different architectures are found in the organic solar cells, and what type of characterizations or what type of instrument we are using for the fabrication of these solar cells. And after that, we will discuss one or two slides about the Forster resonance energy transfer so that we can get an idea how we can explore these mechanism in the organic solar cell. Then we will understand how this FRET mechanism is useful to enhance the efficiency of bulk heterojunction organic solar cell, and finally we'll conclude. Before starting my presentation, I want to give one slide about how this solar energy is important and relevant to the India point of view. Let's see. This is a map which I have taken from NREL site. NREL is the National Renewable Energy Laboratory of USA. And from this map, we have clearly seen that this red region, orange region, and the yellow region shows the solar resources. And when we're talking about the scalability of these solar resources, India is well gifted with this abundant amount of solar energy, which is capable for producing 5,000 trillion kilowatt of clean energy. And in India, there are more than 300 sunny days in a year. So when we see this graph, here are the solar resources, and it shows in a single day, we can, this energy can produce 4 to 7 kilowatt hour per meter square area, solar energy. Now, presently, in India, for the generation of electricity, the major part is utilization of the coal. And when we utilize the coal, it will generate a lot of harmful gases and which can pollute the environment. So when we compare this solar energy in compared to that, this is zero emission. This is safe utilization of energy, and it produces no harmful gases which can affect our environment. And third one is security of the resource. One day all the resources like a coal or all the fossil fuel going to the end. But when we're talking about the solar energy it is the most secure from all of the resources since it is abundantly available. So theoretically, we have needed a very small amount of sun energy to meet our entire current country power requirement. And there is one more figure which can describe that presently we are using 56% of coal for utilization of electricity, but our government took so many good initiatives to utilization of these renewable energy sources, and maybe within the 10 years they will reduce the utilization of this coal to 32 or 33%, enhance the utilization of solar energy. And this slide is a little bit about how the solar power is useful for the generation of electricity in India. Now we are moving on organic solar cell. These organic solar cells are divided into 3 generations. The first generation we called as a traditional generation, silicon wafer generation or a wafer generation. in which we have found a silicon solar cell and polycrystalline silicon solar cell. Presently, more than 80% of the solar market is covered by the first generation solar cell. Now, here is a second generation. We call this generation as a thin film solar cell. It consists with amorphous silicon, cadmium telluride, CIGS solar cells, in copper, indium, gallium, diselenide solar cells. And in the third generation, this is called as emerging photovoltaic technology. And there are so many different technology inside this. First is the dye-synthesized solar cell, then the organic solar cell, perovskite solar cell, and quantum dot solar cell. Here, this is the picture of the Professor Michael Gretzel, and he's the father of dye-synthesized solar cell. Here, this is Professor Alan J. Hager from he has got a Nobel Prize to find the conductivity in the polymer in 2000. He got a Nobel Prize on that. And this is Professor Henry Smith, who first time reported the highly efficient perovskite solar cell. And when we're talking about this technology, technology defines the material. Suppose if I say the organic solar cell technology, the organic material we are using, and if we say the perovskite solar cell technology, we are talking about the perovskite material. So technology is relevant to the material which we are using in this for the production or for the fabrication of solar cells. Now here we will discuss more about the organic solar cell, because this presentation is mainly focused on the organic solar cell. This is the brief history of, this slide represents the brief history of the organic solar cell. First organic solar cell was fabricated in 1978 by T. Fang et al. And they have fabricated a single layer solar cell, which they have placed that organic layer in between the two electrodes. Here you can see in between the IT and the aluminum, and they have achieved the efficiency near about the 7%. But the problem with the organic material is that its diffusion, in this, the diffusion length of the exciton is very low, near about 10 to 15 nanometer, due to which if the exciton is generated far from the interface, they recombine and there is a loss of carriers. Due to this, the efficiency is very low. Later on, C.W. Tang in the 1985 fabricate bilayer solar cell, bilayer organic solar cell, in which first they have prepared a P layer organic material and then the N-type organic material, and they make a sandwich in between the two electrodes. But the problem is same with this, the diffusion length, but they have achieved the efficiency near about 1% and the fill factor about 65%. Later on in the 1955, with the collaboration of U et al. And Professor Alan J. Hager, they have given a new scenario of this organic solar cell that is called a bulk heterojunction, in which they have make a single layer, but that single layer consists of a blend of a donor and acceptor material. They have achieved a very good efficiency, like a 2.9%, with a very low power intensity, like a 20 milliwatt per centimeter square. Now, this is the history of the organic solar cell, and this shows the progress of the organic solar cell with respect to time. And when it started in 2000, 2001, its efficiency was 2%. Now, when we are looking today in the 2020, their efficiency is crossing to the 17%. Here, this black dot shows the fabrication of this solar cell, in which they have used the polymer and the fullerene acceptor. But these blue dots, it shows the fabrication of solar cell with the non-fullerene acceptors. And in the after the 2000s, ending of 2016 or starting of 2017, the last the solar cell which is fabricated with the fullerene acceptor achieved the efficiency of 11%. But after that, the discovery of these non-fullerene acceptors, this efficiency is significantly boosted and achieve and cross the limit of and cross the milestone of 17%. Now let's see these efficiencies on NRA chart. This chart is given by the National Renewable Energy Laboratory. They certified all highly efficient organic solar cells. And here, when we see towards the emerging photovoltaic technology, here the organic solar cell shows the filled circle, red filled circle, and here when we see this shows the 17.4 efficiency. Now, day by day, the people are doing more research to enhance its efficiency and try to reach the goal of 20% efficiency of these organic solar cell. But when we're thinking about why the people are looking towards the organic solar cell in compared to the present photovoltaic technology like a silicon technology, whose efficiency is good and whose lifetime is also good. But there are some plus points in this new emerging photovoltaic technology. Let's see what these are. When we're talking about this organic photovoltaic technology, these are the ultra low manufacturing costs. But it means the cost requirement for the production of these organic solar cells is very low when we compare with the silicon photovoltaic technology. Second, the requirement of the temperature. When we fabricate the organic solar cell, we don't need a high temperature, but when we go for a photovoltaic technology, we need a high temperature near about more than 800 or 900 degrees Celsius. These solar cells, organic solar cells, are lightweight, flexible, and ultra thin. The flexibility and the lightweight of the solar cell is less than 1 kg when we're talking about 1 meter by 1 meter. And the thickness of this solar cell is less than 1 mm. And when we're talking about this is in the more than in the centimeters, like more than 2 or 3 or 5 centimeters, the thickness, maybe more than that. These organic solar cells, you can tune the color of these organic solar cells. It's sometimes you can fabricate as a transparent, semi-transparent also. But when we're talking about the silicon solar cell, there are only two colors, black and blue. We can deposit these organic solar cell on the flexible substrate also, but for the fabrication, we need a rigid or a stable substrate. And then the organic solar cell, the main is that this is environment friendly. The consumption of material is very low in the organic solar cell. It is less than 1 gram material required if you want to fabricate a solar cell of 1 meter by 1 meter. And this is the project. This is the product of organic solar cell. This is a battery charger, and this is developed by the company infinitypv.com, and they have commercialized these organic solar cell in the market. Now, let us discuss about the structure of bulk heterojunction solar cells. What type of structure we are using? Here the picture. This picture shows that this bulk heterojunction, what we call the blend of a donor and acceptor material, that is called an active layer. That is a sandwich in between the two electrodes, like anode and cathode. Sometimes we're using some additional interface layer in order to enhance its collection efficiency. In this, you see, this is a glass substrate. On the glass substrate, this is a transparent conducting oxide. Mostly we are using the ITO, indium tin oxide. And on that, here you have seen this P.PSS. As I say that sometimes we use some interface layer. This is called a whole transport interface layer, and this is an active layer, which is a blend of donor and acceptor. And above that, this is a metal electrode, we call a cathode. This is a conventional configuration. And there is one more configuration that is called inverted, when we reverse these things. When we place this HTL here, and in the conventional one, this ITO act as an anode, and this is act as a cathode. But in the inverted one, this is act as a cathode, and this upper electrode act as an anode. When we zoom this, here we have seen in this film, there is a 3 type of phase we get. First is the donor phase, second is the acceptor phase, and one is a mixed phase. And when we incidental light on it, there are generation of exciton, and there is a diffusion of exciton, and they goes to the charge transfer state. And in the charge transfer state, they dissociate and converted into free charge carriers. But if the exciton generated in a place where it is not able to find interface for the dissociation, then it goes under the recombination. That recombination is called a geminate recombination, when exciton didn't find any interface. But if they recombine after the dissociation, that interface is called the non-geminate. Sometimes we call that as a bimolecular recombination. Now let's see this interface, how these charge carriers are moving towards the respective electrodes. This is the picture of one interface. This is the donor. This is the acceptor. And when this, we have applied a simple load just for making a schematic diagrams. And when we incidental light, the exciton is generated, and they diffuse towards the interface, where they find the charge transfer state, and they dissociate with each other and move towards the respective electrodes. There are the 5 steps. First, the photon incident, then exciton generation, exciton diffusion, exciton dissociation, and the charge collection by their respective electrode on their respective electrodes. This is just an overview of the structure and the working mechanism of bulk heterojunction solar cells. Now, how we can fabricate these solar cells? For the fabrication, we require materials, and first material we need a substrate, like a glass which is coated with the ITO, and like this, coated with the ITO. And after that, we can develop a pattern of this ITO by using a laser or by going with the chemical etching, wet chemical etching, so that we can develop a electrode or develop a mask as per our requirement. And after developing these strips of the ITO, the next step is to clean this substrate, which is very required because the active layer thickness is near about 100 to 200 nanometer. If your substrate is contaminated with the dust, whose size in the micrometers, they can damage your device. So first step is to clean the device, and after cleaning, you can go for fabrication of this device. You place your substrate on the spin coater. Spin coater is looking like this. When we zoom this spin coater, you see this is a chuck where we place this substrate, and this is a controller who can control the speed of this chuck and the time by placing or by setting its moving speed. We call that as RPM. With this RPM, we can set the thickness of this active layer or the layer which we are going to deposit on it. And we can use a pipette and drop our solution. This first layer we will get as a whole transport layer. On the whole, after depositing this, we will anneal this. Sometime we will anneal this layer, and then we will go for deposition of another layer with the help of spin coating, that is called active layer. On the active layer, sometime we deposit the active layer. Sometimes we deposit the ETL, electron transport layer, but sometimes we can directly deposit the metal electrode on it. But these active layers look like these, as I have shown. And after that, we will place this substrate in the thermal evaporator for the deposition of metal electrode. And these are the metal electrodes. Aluminum. Mostly in the conventional structure, we are using aluminum and aluminum. And for fabrication of inverted, we are using metal silver as a metal electrode. And here, this cross section shows the pixel. This is the main who will give us a characteristics of a solar cell devices. These cross sections are the pixel, and these are called the solar cells. And from these cross section, we will get our IV characteristics. And these represent the size of this ITO strip and the size of your upper electrode, top electrodes. And your active layer is a sandwich in between the two in between the two electrodes. And then we will go for the characterization. And the characterization, we shine a light on it and collect the IV characteristics of this. This is a fabrication process of organic solar cell. Now, this picture gives the summary. First, a summary of fabrication of organic solar cell. First, we need some material, need a material which we are going to deposit, like a donor acceptor, some electron transport material, whole transport material, then ITO electrodes, ITO coated glass substrate, then electrode material, top electrode material. The first step is we are going for a patterning the substrate, pattern as per our requirement. Sometimes we go for a strip, or sometimes we go for some other structures. And then second step is cleaning. Basically, we are going for two types of cleaning. One is a soap, and second is a chemical. In the soap cleaning, we are using the lab soap, and after that we go for a chemical cleaning. In the chemical, we use cleaning with the acetone and the cleaning with the propanol. After that, we will put our substrate for a dry in the oven. And after that, we are going for a UV cleaning. UV cleaning is very good for the organic solar cell because it removes the organic impurity and increase the wettability of your substrate. So you can deposit any type of material, and it will stick well with your electrode. And then we will go for a spin coating for a hole transport layer or electron transport layer as per your configuration of your device. Then we can deposit a top electrode with this evaporation system, thermal evaporator system, and then finally we encapsulate our device. Now, after encapsulation, we go for a characterization. In the characterization, we get a curve like this. This is a dark vector 6, and when we shine a light, it gives a photocurrent. And when we vary the voltage, the photocurrent moves like this. And these characteristics are obtained in the fourth quadrant. The light characteristics are obtained in the fourth quadrant, means that your device is delivering or generating power or delivering power to the load. And from these curves, we get some parameter like VOC, VM, maximum voltage, JSC, GM, and maximum power. From this, we can calculate their fill factor and their efficiency of the device. And I also want to show sometime we are going for a real-time measurement like this. We place our these devices on the window, and with the help of this, we can calculate their real-time either a voltage or a current with respect to times. And this is a very good instrument. We can measure more than 10 devices in the single shot, and we can collect the data, continuous collection of the data up to 1 month or 2 months with a 20 minute difference in each day. The mean is that we can collect continuous data simultaneously for more than 10 devices with this instrument. Now, this is my achievement. I have achieved very good efficiency in organic solar cell is a 9.43. These devices are fabricated inside a globe box. The globe box is uncommon name for you, but I will explain later on. And in this, I have used this polymer PTV7TH and PCBM, P71BM. This is the absorption characteristics. And with the help of some additive like a DIO, I have achieved the efficiency from 5%, near about 5% to the 9.43%. Oh, these are all equipment which we are normally using for the fabrication of solar cell. I said previously, I said a globe box. Globe box means there is a box who is filled with nitrogen connected with the globes, which are used to work inside these boxes. And if you fabricate your device completely inside the globe box, the lifetime of your device is increased, because when you prepare your cell in the open air, they will start to degrade in the starting, because oxygen and the moisture is the enemy of the active layer of the organic solar cells, enemy of the organic material when we are going to fabricate your devices. So if you want to fabricate a good and efficient and long time running device, you need to use a globe box, so that you can start a spin coating process from this chamber and from this chamber, and finally you can deposit the electrode also inside before without moving out of your device. But if you want to fabricate your devices outside, you need a spin coater, as I've shown previous slide, and then you can need a thermal evaporator for the deposition of metal electrode. Here you have seen there is a yellow color, and here there is a yellow color. This is a red hot of boat, red color, sorry, red color, red hot boat. Here what we are doing, we are using two electrode. In the two electrode, we are placing a boat, and we will apply a high current. With the high current, the boat start to red hot, and the material which I have inserted in this boat start to melt. And finally, they got a temperature at which they start to put it, and we get our top electrodes. This is a solar simulator, and this is a laser which we are using for the patterning. This is the PS measurement, and this is the absorption measurement of active layers. Up to here, we have discussed about the organic solar cell, how it works, and how we can fabricate these solar cells. Now we are moving towards the FRET. What the FRET is? The FRET is the Forster resonance energy transfer, or sometimes we call this a fluorescence resonance energy transfer. This phenomena is given by the Professor Theodore Forster. He was a physical chemist, and they have given this mechanism in the 1946. But the mechanism means that one molecule transfer their energy to the another molecule by using a non-radiative mechanism. And in this phenomena, the donor molecule is either a dye or a chromophore that initially absorb the energy and then sequentially transfer its energy to the acceptor chromophores. And when they have transferred their energy to the another molecule, there is a reduction of its own intensity, its own fluorescence intensity and the excited lifetime. But on the another side, there is an increase in the acceptor emission intensity. These are some introduction about the FRET. FRET is also a distance dependent mechanism, so that when they are close to each other, like distance from 10 to 100 nanometer, 10 to 1000 angstrom, 1 to 10 nanometer, they can easily transfer their energy to the another molecules. But we also need some primary condition for the FRET. The main primary condition is that there is absorption spectrum should be overlap with the fluorescence emission spectrum of the energy donor. It means the absorption spectra, who will get the energy, the molecule get the energy acceptor, should overlap with the emission spectra of the energy donor. So when the donor emit their energy, your acceptor should become in the range so that it will absorb their emitted energy non-radiatively, mostly non-radiative. Now this is the diagram which described the budding which I've seen shown in the previous slide. And here you have seen that when they are not in the range of the FRET, they have their own emission spectrum, but they come under the FRET. This donor transfer their energy to the acceptor, and the acceptor emission intensity increases. Emission intensity start to increase. And this equation represents how much close they need for so that they can transfer, the molecule can transfer their energy from one to another. That is called the Forster distance. Now, for that, as I've shown that for energy transfer, we need two molecules. One can transfer their energy and the other one can accept their energy. For that, in organic solar cell, we need, for the FRET, we need a ternary organic solar cells. Now, first we need to know what is the mean of this ternary. Initially, the organic solar cell, which we have seen, bulk heterojunction, that is, there is only one donor and one acceptor. But the main problem is that the donor absorption spectra is very low. Absorption range is very low. Here I have seen the donor 1. Here you have seen the donor 1, whose absorption is in this range, and another donor is here, whose absorption in this range. And due to this new narrow absorption, we are not able to achieve a very good efficiency. Then the researchers thinking about a new architecture, they have given that tandem structure. In the tandem structure, we can prepare one cell with a high band gap polymer, another cell with a low band gap polymer. Then they connected these cells in the series. But for the connection of in series, they need interconnecting layer, but this architecture is a little bit complex. Later on, they think about why we are not adding both donor 1 and donor 2 in a single blend. So they have tried and they have achieved a very good efficiency in that. And this, in the ternary blend, they have either used a 2-donor single acceptor or single donor 2 acceptor materials, but preferably the device which have shown the good efficiency in which they have using the 2-donor and single acceptor. By using these 2 donor combined in a single blend, you see in the blue part, the absorption spectrum is increasing due to this. And in the ternary blend structures, basically they are the 4 different type of mechanism has been found. Suppose the first one is that in which they are representing as a cascading energy, another donor act as energy level, which can help to transport their charge carriers. And in the second mechanism, both the donor generate the charge carriers separately. That is called a parallel linkage mechanism. In the third, both the donor, when we combine together, they act as an alloy and they can generate the charge carriers. But the main is that in which the FRET is occur, in which the one donor transfer their energy to the another and increase the number of charge carriers or of electron, and which overall enhance the efficiency of the device. Now, let us start the research. I have begun my research in 2011 on this turbulent structures. At that time, I have found a few of the paper who have achieved the efficiency near about the 4%, in which they have using the P3HT, PCBM, and they have added the third component like polymers. But these polymers blend are not able to achieve the high efficiency, but they have achieved the efficiency near about the 4%. But at that time, I have used new polymers like a PTB7 and PCDTBT, and I have achieved the efficiency near about the 6%, and we have filed a patent. And that was the first patent of this type in that year. In the 2016, I have our patent that has been published, Indian patent in Indian journal. Our patent has been published, and in 2018 we have got a patent grant. And in 2017 we have also published as the our work has been published as a UK patent. Now, what I have done in this patent, let's see. As I said, I have used a new polymer like a PTB7 and PCDBT, and from here you have seen this absorption spectrum. This absorption spectrum is of PTB7, and this is for the PCDTBT. And when we blend together, you can see there is a modulation of their absorbance. And when we have fabricated these devices, we have achieved the efficiency near about the 6%. Here we have varied the concentration of the acceptor, and here we have varied the concentration of this PCDBT, and we have find out a suitable concentration on which we have achieved a good efficiency. Here the curves are not good, but later on we have done more work and we have added some additive. Because of that, we have got a good curves and good morphology from here and achieve the efficiency near about the 6.5%. Up to here, I didn't know anything about the FRET, but in 2013, I have found a paper. In the 2013, I have found a paper in which they have described the Forster resonance energy transfer in bulk heterojunction solar cell, in which they have used a P3HT as a donor, energy donor material, and the SQ dye as a energy acceptor material. And as I've discussed earlier, the requirement for the FRET is that your emission of your energy donor and the absorption of your energy acceptor should be overlap, and they have shown here. There is also, when we add the energy acceptor inside the energy donor, the emission spectra of the energy donor material like a P3HT start to reduce, and the emission of energy acceptor start to increase. And when we add this energy acceptor in the energy donor, their excited state lifetime is also decreased. And they have shown these characteristics to explain the Forster resonance energy mechanism. Initially, without this mechanism, they achieve the efficiency 3.27%, but when they blend together these three components, they have achieved the efficiency near about 4.5. They have reported the 38% enhancement in the efficiency. I have strongly inspired by this paper, and I have started to explore my results. And again, I have tried to fabricate the devices. In this time, I have replaced my acceptor. I have used the PC71BM, which has a superior performance as compared to the PC61BM. The same, you see the absorption and the emission curve. This curve shows the normalized absorption, and there is a modulation of the absorption spectra when we add these two components with a different concentration. And this is the absorption spectra when we add a PC71. Here you can see this is a flat absorption up from 750 to 320 or 330 nanometers. And then we have fabricated the devices with this configuration, and we have achieved the efficiency near about 8.9% on the concentration of this. Here we have also measured this EQ spectra of this solar cell devices, and this is the structure of solar cell. We have used a conventional device structure in which on the ITO we have deposited the HTL, then active layer. Active layer is a blend of ternary components like TV7, PCDT, and PC71BM. And later on, we have investigated the FRET mechanism inside this. And here you have seen this yellow region shows the overlap of the absorption, this blue line absorption of the energy acceptor, and this red portion is the emission of the energy donor, and this is the overlap region. Same we have seen, this is the emission spectra of the energy donor material, PCD-TBT, and when we add energy acceptor PTB78, its emission has gone, and the emission of the energy acceptor start to increase. Same here when we see the excited state lifetime of our material. When we blend together, normally when we see the PCD-TBT, which is energy donor, its a lifetime is very high, like 475 picosecond. But when we add energy acceptor inside this, its lifetime decreases less than 20 picosecond. Here it's a 40 picosecond and a 7 picosecond. And from this lifetime, we have calculated their FRET efficiency. The formula for calculation is 1 minus tau dA. This is the lifetime of a donor receptor blend, and this is the lifetime of a donor. From this time period, we have got the efficiency near about 96 to 97%. So it shows that this PCDVT transfer their energy non-radiatively to the PTB7, and there is a increase the generation of the charge carriers on the upper state, and which overall enhance the efficiency of the device. Further, we have explored this with the transient absorption spectroscopy. This is a little bit complex method, but I will give a little bit introduction about this. This is a Jablonski diagram which shows that different mechanism. When we shine a light, the electron is going to excite from ground state to the excited state within the 10⁻⁵ seconds. It's a femtosecond process, and after this vibrational reaction, it comes to the ground state with the different mechanisms. And in the FRET, in this transient absorption spectroscopy, in the place of absorption, we are getting a ground state bleaching. This is a steady state mechanism in which steady state means there is no change in the time, only change in the wavelength. But this is a transient because this is measurement of absorption with respect to time also. That's why this is a optical density. This is a ground state bleaching, stimulated emission, and photo-induced absorption. Here, this shows the transient characteristics of PCDVT. This is the PTB7. This is the ground state bleaching, and this is the photo-induced absorption. Again, this is the ground state bleaching and photo-induced absorption of the blend. Here we have noticed that when we blend together, this photo-induced absorption increases to the 40. And here it is less than 20. This is a signature of the energy transfer, and we have seen this signature in the 3D view also. Here there is no signature of energy transfer individual, but when we have blend together, there is a signature of energy transfer in this region. Because this is a photo-induced absorption, and the different optical density is high, which shows that there is a large number of the charge carriers are available in the excited state of the blend of these PTB7 and PCD. And finally, we have calculated the Forster distance, so that we have find out that how close both this acceptor and the donor material to each other, like a PCDVT and PTB7 to each other. From this equation, this QD represents the quantum yield of the donor, N is the refractive index of the blend, and FD, this epsilon A represent the molar extinction coefficient, FD is the donor emission, and from this equation we have calculated the Forster distance, that is near about the 7 nanometer. We have used a software like a PhotoChem CAD in order to calculate this, but individually we need to calculate this parameter first, then we fill this parameter, the software calculate this Forster distance, and we have found in this the Forster distance is a 7 nanometer. Normally range is from 1 to 10 nanometer. And finally, we have published this paper in the Advanced Material in 2015. This Vinny Gupta and Suresh is my co-supervisor, PhD co-supervisor, and this is the Professor Alan Jager, who got a Nobel Prize in 2000 to find the conductivity in the polymer. Later on, we have also studied the compatibility of both the polymers. In order to understand the compatibility, we have go for the charge transfer mechanism, and for that we need to fabricate a single carrier device first. We need to understand what the single carrier device is. In the single carrier devices, there are the two types. One is the hole only device, and the second one is the electron only device. When we're talking about the hole only, we can place this metal electron near to the HOMO level, and we're talking about the electron only device. We will place this, shift this metal electrode towards the LUMO level. But here we have fabricated the hole only device because these are the P type of material. So we need to study the transport of the carriers toward the HOMO levels. This will give a curve when you go for charge transport study. This is a simple IV curve. We have made this a log plot. And here we have seen the region A, B, and C. A region is in the starting when you increase the voltage, it's a ohmic region. Then there is a trap limited SCLC region. Then there is a trap free SCLC region. SCLC trap limited means, as we know that organic materials, there are so many defects. These defects are called as a trap. And when we inject the charge carrier, the mobility of these materials is very low, so that it will generate a space charge region in between that. Due to that, it will block the further injection of the charge carrier. But when we increase more and more voltage, the injection of carrier increase, and we will finally achieve the trap-free region in which all the traps which are present in the organic material are filled. And after that, when we inject, one electron inject inside and one electron we will get out. That's why we call this as a trap-free. And from these equations, we have calculated some parameters like a mobility. From here, we can calculate a mobility, and from here, we calculate a trap density. This voltage is called a critical voltage. And from this equation, we have calculated some parameters. These are the IV characteristics I have described before. And you have seen that we are using a hole-only device. The hole is moving through the HOMO level. Here also, hole is moving through the HOMO level. The charge is moving through the HOMO levels. And they have broke the conduction through the LUMO levels. And from there, we have found that when we make a blend, its efficiency, its mobility enhances, and there is a reduction of the trap densities. And when there is a reduction in trap density, means maybe there is a reduction in the recombination also. In order to understand the recombination, further I have studied the GSC with respect to the light intensity and VOC with respect to the light intensity. When I have studied the GSC with respect to the light intensity, this is the relation, direct relation. And here, when this alpha value is very close to 1, it shows there is a reduction in the bimolecular recombination. From here also, this value of the slope, kT by Q, this is in between 1 kT by Q to the 2 kT by Q. And when it away from the 2 kT by Q, it shows that there is a reduction of the trap density. And from these analysis, we have found that there is a reduction in the traps, and due to the reduction in the trap density, there is a reduction in the recombination, and there is an enhancement in the efficiency of the devices. And we have published this paper in the applied physics letters. Later on, I have continued my research and I find a new highly efficient polymer, and I did the same thing on that. In that case, I have got a PTB7TH polymer. PCDTBT remain the same, PC71BB remain the same, but the change is the PTB7, and I have achieved the efficiency of near about 10.7%. This shows the modulation of absorbance when we blend together, and we have also find out the fret inside this. This region, yellow region, shows the overlap region of absorption of the energy acceptor to the emission of the energy donor molecule. And this is the schematic diagram of the flow of the charge carriers. Here PCDVT release their energy. From this, it get energy excite of the carriers. And this is a simultaneous process. When they recombine or when they release energy, it excite. This is a simultaneously. And this is a non-radiative process. From this, there is a number of carriers has been increased in the upper state. And here we have fabricated the devices in the inverted type configuration. Inverted configuration. Here I have shown. This is the inverted type configuration. So I have used the ETL on the downside. And then we have also studied the PL. Here you have seen this is the PL intensity of the energy donor material. And when we add the PTB7, its emission disappear, and here the emissions start to increase. The lifetime is also decrease. The lifetime of the PCDVT decrease when we add a PTB7TH, and from here we have calculated the energy transfer efficiency, which is 93.6% to the 97%. And again, we have calculated the Forster distance, which is dependent upon the so many parameters. First, we need to calculate this parameter, and with the help of the software like a photocam CAD, when we fill these all values, we will get this final distance, Forster distance, that is near about 8.7 nanometer in this case. But still, some of the research is pending on this work, and that's why I'm not published this work till now. Now, this is the final slide of my conclusion of all the work which I present in this presentation. In the starting, I have shown you a figure. Now, I hope you understand that this PCTBT is energy donor and this PTB7 as an energy acceptor material. When they are posed together, less than 10 nanometer, this molecule transfer their energy so that its emission is reduced from here to here. Its emission is reduced, and here emission is increased. And here you see the number of electron has been increases. Similarly, in the case of PTB7TH, this is the emission of the PCTBT, and this is the emission of the PTB7, which is very low. But when they are interact with each other, this PTB7TH emission enhances, and we show the signature of the FRET, and there is a reduction of the emission of the PCTBT. Finally, here also there is a number of electrons increases. Now, this overall presentation shows that how the FRET enhances the efficiency of organic solar cell from first 6.8 to 8.9% in the case of PTB7, and then up to the 10.7% in case of the PTB7TH. But when we use this polymer, new and new polymer, and with the combination of newly developed non-fullerene acceptor, which is also a polymer, we are able to achieve the efficiency near about to the 20% of that. So that our FRET resonance has been moved from ultraviolet region to near IR regions. Thank you to all of you to listen my this presentation. Thanks to the organizer who has invited me for this presentation. Best wishes to all of you for your future research. Thank you. Thank you very much.